So as I mentioned before, we're really not doing anything new. So if you do have questions on anything lab-wise, exam-wise, or questions or something I can help you with, be more than happy to answer those. So just let me know.
Um, yeah, so
Yeah.
on experiment, what's experiment? 12? Yeah. Um, so for finding the pressure of the collected gas, do I just subtract the barometric pressure to the height difference that I found from the water?
So that would be like number 5 on the table. Is that the one you're talking about?
Yes, number 5.
So yes. So
Okay.
that would be the barometer pressure, and then he should have done like a measurement of the height difference between the water and the sort of the water level in the tube,
Hmm.
and that's what you would subtract off. You need to convert it though the millimeters of water into millimeters of mercury by using that like 13.5 conversion that's in the introduction.
Yeah. Okay. So I was correct on that. And then, so for number 7, for trying to find the dry gas,
Mhm.
what am I doing there? I'm a little confused on that part.
Yeah, so there's actually like two things sort of going on in this experiment. The one thing was what we just talked about, which was in a normal sort of experiment. At the end, you would take that tube and kind of go up and down to equalize the pressure inside and outside of the tube, and that's what the sort of subtracting off the millimeters of water to mercury, sort of that height difference. The second thing that's going on is what we talked about. Whenever you sort of collect a gas in this process, kind of like what was going on in there in water, right? So as the gas goes in, you end up with the gas that you're interested in, which in this case was hydrogen, I believe, right? So I think that's what.
Yeah, it was the hydrogen gas.
But because of the process of you did it in water, the reaction itself, as it's taking place, so you have that magnesium that's kind of reacting and creating all that hydrogen gas. It's going to also convert some of the liquid water into basically water vapor or gas, right? So what you end up doing here is you now have like a partial pressure situation where the total pressure is the pressure of the hydrogen gas, which is really what you're interested in, plus the pressure of the water vapor that was really just a byproduct of the reaction taking place in water. And so you just got to do a simple sort of subtraction where you would take the total pressure minus the vapor pressure of water. And this value, which is the vapor pressure of water, is found in a table in the back of your book, your back of your manual. Yeah. And will be based off of probably the temperature. And this number here is a number we were just talking about, which was number 5. Yeah. And when you do that, that's why they call it dry gas, because you're subtracting off the water pressure or the pressure associated with water. So that's why it's called dry gas at that point.
Okay, okay. So I did that part correctly as well. I was just I was a little confused because I did find the vapor pressure for water. I was like, yeah, what do I do now? And then I just confused myself. And then after that, finding like the experimental constant for the ideal gas law, all I would do is try to find uh R, right?
Exactly. So you rearrange the ideal gas law to solve for R. And
Okay, and
at this point, you should have the pressure. You should obviously have the temperature that needs to be converted to Kelvin. You
mhm.
should have the volume of the gas that was collected. It needs to probably be converted to liters. And what am I missing there? PV. And you need the moles of the hydrogen, not the magnesium, but the moles of.
Oh, okay, okay,
So that's going to
and
require the balance equation, the stoichiometry.
okay, and the moles, or sorry, not the moles. The the dry gas is the one that I put into
Yeah, so
the equation.
you
Okay.
want to definitely use that. Obviously, convert it to atmospheres, but you definitely want to use that one because that has basically all the corrections that you need to do. The first one for the sort of the pressure difference, and the second one for getting rid of the water vapor pressure. So that very last number that you got, which again needs to be converted to atmospheres, is sort of really at this point ideally just the pressure of the hydrogen gas.
Oh, okay. All right. And then I have one more question, and this is for the pre-lab. for number 3. I know we went over it a little bit before, um, but I'm still a little confused about it. So do I take the what you call it, the height difference divided by 13.5, and then I find the millimeters of mercury, and then I subtract that to the pressure that is found already, so I can get the dry gas?
Yeah, so I'm gonna take a quick peek. Remind me. Sounds right what you're saying. So we got the same setup as the experiment. Water level is higher. So you just said you're going to subtract, right? So that's good. Are you doing anything after you subtract that?
So hold up. Um, yeah, I'm not quite sure after that, besides changing the temperature
Yeah,
to Kelvin, and
you
then
wouldn't.
just doing
This is actually just like we were just talking about on the table for the
uh-huh.
experiment, where you would uh, use
Oh,
use the vapor pressure of water. It's the exact same thing. So how you just figured out the dry pressure for the experiment would be how you would do it for here too. That's why
got you.
that's why they give you the temperature so you could go to the table and look it up in the correct temperature.
Yeah, I thought it was weird that I was changing um that because it's just saying the temperature of the water.
Yeah.
Okay. And then with that, um wait, and then you'd grab this pressure and subtract it from the pressure that you found from minusing the height difference from the water to the pressure that is in the problem.
Yeah, so you basically need to
Okay.
do the two corrections. So one for the height difference and then one for the vapor pressure of water. Just like
Got you.
just like we just went over there in that table exactly. Just use the other numbers, obviously.
Yeah.
That's not a
Yeah.
problem. Yeah,
Okay, sweet. Thank you for that.
you're welcome. Other questions I could help anybody with?
I have some questions about the chapter 9 homework.
Sure. Um, you want to tell me what the questions are? I'm not sure I have the book with me, as bad as that sounds.
No, it's okay. I just am having a really I feel like I'm really maxed out on my chemistry learning and I'm just having a hard time getting these last couple chapters whatsoever.
okay. You kind of cut out there. So was there something specific in terms of a topic or?
Yeah, the first question is asking about like the intermolecular forces, and I know we're supposed to be able to determine like H bonding, dipole dipole bonding, and dispersion forces or whatever. How do you go about even determining which ones are which?
So they basically those three basically go. The best way to sort of determine it is based on sort of polarity, if you will, of the molecules that are involved. So when you think about those three guys, which is basically hydrogen bonding, dipole dipole, right, and dispersion forces. First off, dispersion forces are those really weak forces, and they're temporary forces, and they're really for guys that are nonpolar. And those are the guys that is when a nonpolar molecule wants to interact with another nonpolar molecule, either itself or a different sort of nonpolar molecule. And that's because these guys normally don't have charges. So something has to occur to these guys to temporarily gain a charge so that they could have an attraction. And it's only temporary, which is why these are really weak and why we see it with nonpolar molecules. So if you could determine that whatever you're looking at, if you're asked like, hey, you know, what type of force would this guy sort of use? If you draw a Lewis structure or just understand that carbons and hydrogens are nonpolar, he's going to be using this dispersion forces because of that. Now, that leaves us pretty much these two guys, which basically are polar molecules are involved. And this is really the forces that polar molecules use. And really, all intermolecular forces really boil down to a basic attraction of a positive side of a molecule to a negative side. It's really that attraction that happens. Now, in a polar molecule, when you do have a polar molecule, basically a polar molecule means that you have a fixed side that's positive and a fixed side that's negative, like water. When you look at something like water, heading towards the, when it has a dipole moment, heading towards the oxygen side of water is negative, the hydrogen side of water is positive, and it's fixed that way, always going to occur. So when you have are dealing with something that is a polar molecule, it is most likely going to be one of these two guys as their main sort of sources. So what is really the difference between these two guys? Hydrogen bonding involves a bond between hydrogen and nitrogen, oxygen, and fluorine needs to be involved. So something like water that is polar, where this guy's more negative and this guy's more positive, it has that bond between oxygen, hydrogen, and oxygen here, oxygen and hydrogen here, basically, and that's that hydrogen bonding ability, and that's going to allow this guy to hydrogen bond. So hydrogen bonding, which is the strongest, is for a polar molecule that has this type of bond in it and has the ability to hydrogen bond. Now, dipole dipole is a polar molecule that really does not have the ability to hydrogen bond. So that's the slight distinction between those two guys, is whether or not the thing can hydrogen bond or not hydrogen bond. So for example, if we took, let me think here, let me do something like maybe we'll do maybe something like this here. Something like this. This is going to be polar, right? It's symmetrical geometry, but we don't have all the same things here. So this guy's going to be polar. Even though it has a hydrogen, this hydrogen is attached to carbon, which means it cannot hydrogen bond there because it needs to be a hydrogen that's attached directly to a nitrogen, oxygen, or fluorine. So even though it has a hydrogen, it cannot hydrogen bond, but it is polar. So he would use dipole-dipole interaction because of that. So that's sort of the differences between those three guys. Hydrogen bonding, dipole-dipole are really for polar molecules, how they interact with themselves and other polar molecules. And again, the distinction between those two is, can it hydrogen bond? If the answer is yes, then it will do hydrogen bonding. If it doesn't have the ability to hydrogen bond because it really lacks a bond between hydrogen, nitrogen, and oxygen, or fluorine, then it will do dipole-dipole. And then if you're dealing with something that's non-polar, that's pretty much dispersion forces. So sort of the polarity of the molecule is really a big helpful way of understanding sort of what intermolecular force would be used. This guy is the strongest out of all three of those. This guy is the weakest. And dipole-dipole is relatively strong, but it's less strong than hydrogen bonding. Technically speaking, hydrogen bonding is actually a type of dipole-dipole, but it's much stronger, so it gets its own sort of classification.
So when we're dealing with these big giant molecules, instead of like, you know, some of these ones that are a little more familiar looking, how are we supposed to go about determining if it's, you know, dipole-dipole, hydrogen bond? I mean, they're massive.
So you want to look at what they are. So if they're big molecules, perhaps there are a lot of carbons and hydrogens, maybe.
Yeah, like CH3, CH2, CH2, NH2.
So CH3, CH2, CH2 is NH2. Yeah. So what you want to look at is, the other thing that sort of helps you decide that is there a part of the molecule that can do one of those things? So in this guy, which is like an organic guy, this is an amine, and this part of the molecule here, that's all carbons and hydrogens, is pretty much nonpolar. Now, when we look at NH2, NH2 is really like a derivative of ammonia. And ammonia here has the ability to hydrogen bond because there's a bond between hydrogen and nitrogen, right? You need either a hydrogen nitrogen bond, hydrogen oxygen bond, hydrogen fluorine bond in order for hydrogen bonding to occur. So it could occur. So when we sort of zoom in on this part of it, although this part over here really is nonpolar. At best, is going to do some dispersion forces. But what's really going to happen here is this part, which, if you draw it out, actually kind of looks like ammonia here. And it has a bond between nitrogen and hydrogen. And that means that this guy would have the ability to actually hydrogen bond because of that. So on those really big guys, and most of the time, if you have these really big guys given to you, they probably will have a lot of carbons and hydrogens. They're pretty much organic guys. So what you would want to look on those guys is there a part that can do either hydrogen bonding or dipole dipole? If there's not, then it's probably going to be dispersion forces. So you could have like a giant, like, thing like this, and if you look at this entire thing, there's absolutely nowhere that anything other than dispersion forces can occur with this guy. They're all carbons and hydrogens, and it would be pretty much dispersion, nonpolar interaction. In the case of a lot of organics, you will cross this sort of thing. I think we talked about maybe towards the end of the previous chapter as well, that in some of these organic guys, you'll have sort of two parts to the same molecule. One part might be nonpolar, the other part might be polar. And if you do again have that polar part, it probably would have the ability to either hydrogen bond or do something like dipole dipole interaction. So for example, if you had this, you know, something like this, you could look at this again as this part really not going to do much other than some dispersion forces because it's nonpolar, but this OH bond here is a bond between hydrogen and oxygen. It is going to be a polar bond, and it will be able to hydrogen bond, through that with another one of itself or something else. Now, there is a limit to sort of how well that will work. So if you had a giant organic guy, in terms of solubility, for example, if you had a giant organic guy of this, pretend this line is just all carbons and hydrogens, so I don't draw it all, but basically it's just a big thing like this. And at the end, you just had this one lonely OH group at the end. Technically speaking, it could hydrogen bond there, and it probably wouldn't be able to do so because with something like water, for example, because the majority of that molecule is pretty much nonpolar. So it most likely would be doing more dispersion forces than that. So things like solubility will start to decrease a lot when you build out that really long chain. So you want to be looking for those. And again, it's very common that they'll give you some of those like organic type things, areas where, you can either see dipole dipole happening, or most likely most of it would be like hydrogen bonding. And if he does have an area like that and the thing's not ginormous, it should have the ability to do so.
Thank you so much.
Boiling is a cooling process.
Yeah, so it's a cooling process because kind of like very bad boiling thing here. So as we're sort of heating it from the bottom, basically, so we're heating from the bottom. And if you ever like put a thermometer in a boiling water, right, it goes to like 100 degrees Celsius, an ideal situation. And it actually doesn't go higher or lower when it starts to boil. It shouldn't. It's to kind of tap out. And depending where you're at in terms of atmosphere and pressure and stuff like that, it may not get exactly 100. But once it starts boiling, it actually won't go any higher in that. And that's really because it's sort of a cooling process out the top. So even though we're heating it at the bottom, it's actually cooling as it goes out the top. And that's because these guys got to break apart from all these bonds, right, to boil. So they're moving and moving, and you're taking out a lot of that really high energy guys out of the solution. So it's kind of cooling the overall kinetic energy of the solution. And as they try to make their way out, they eventually get out here. I'll draw my circles. They eventually get out in the top there as circles, but they did exert a lot of energy to kind of get out of the solution. So they're going to actually be moving a lot slower than everybody else that's in the air. And it's actually going to lower the overall sort of kinetic energy of the surrounding air and stuff like that. So although it seems kind of like a weird idea, it's actually sort of a cooling process. And it really explains why, again, if you ever solve that sort of thing where like sometimes people are concerned with their thermometer, like it's starting to boil, is it going to break? If you ever looked at a thermometer, they usually go like 100 and then maybe there's another dash after that, like 105 maybe, and then it's the top of the thermometer. And people are usually concerned because it's like, oh, I'm up here and it's boiling, is it going to like go through and break my thermometer? And it won't do that because again, just as quick as it gets heated from the bottom, you're kind of cooling the solution from the top part of it. And again, it's sort of a loss of that energy that's leaving the solution. And even the surroundings is gaining all these kind of slower moving molecules. And overall, it's sort of a cooling process in that sense.
So not only is the water getting cooler, I mean, in a way, also the air surrounding is getting cooler too.
It is it's getting it's cooling in the sense of like energy and stuff like that because you got these slower moving sort of guys that just escaped all those bonds, right, to get out of the liquid part. So overall, the sort of kinetic energy of the surroundings actually lowers down. So in that sense as well, yeah, it's kind of cooling down the surroundings as well.
I see. Thank you.
Can you go over how to find the boiling temperature with molality?
Yeah, so like the boiling point elevation sort of formula.
Yeah. So
So
like the first one for the lab.
the specific one for lemma.
Oh well, just in general,
Yeah,
just to go
just in
over.
general. Yeah. Okay. So basically, it's this equation, right? Changing the boiling point temperature is equal to the molality times the Kb constant, and this is for non-ionic solutes. So guys that basically don't break apart into more than one thing when it goes for a swim. Remember that when we do have something that's ionic, you need to insert that von Hoff factor into there, which is the I. And the difference is, for example, if you did something like glucose, which is basically carbons, hydrogens, and oxygens, that's all going to be sort of molecular bonded to each other, going to be sharing covalently bonded. I guess what I'm trying to spit out there, going to be sharing of electrons and all that kind of stuff. So when it goes for a swim, basically in water, you basically get just one glucose molecule per glucose molecule, which means technically speaking, I would equal one, which is why we don't actually use it here. Now, if you did something like sodium chloride, for example, when that goes for a swim, it's going to break apart into a sodium ion and a chloride ion. And you're actually going to get like a 2-for-1 still here. You can get basically two ions that are going to be formed. I would equal 2 in this case. And remember, that's important because colligative properties, which is like boiling point, freezing point, all those type of things, they're based off of how many particles are in the solution and stuff like that. So the more particles, the more sort of change you're going to occur in things like freezing point, boiling point temperatures and stuff like that. So the first important thing is to identify, is the solute or whatever is being dissolved in that solution ionic, or is it really non-ionic? And if it's ionic, you need to figure out what the I value is. So let's just, for example, say we did we had a sodium chloride solution, and let's see here. Where that thing goes, like far here. Okay, and let's just say we had a zero. Oh, I won't do the one that's in the lab. Let me do 0.950 molality. And actually, let me just do one that's different. Calcium chloride. Let's do that one. That would be different. And let's say we had this solution here and we want to figure out what the boiling point sort of temperature would be. First off, we would want to obviously identify this as calcium chloride, which is an ionic solute, which means it is going to basically um, break apart into multiple ions. So when we look at calcium chloride, it'll break apart into a calcium ion and two chloride ions. And again, that's one calcium, two chlorides, which means technically I is going to equal 3 in this case. And we would want to use this version of the equation, and I is really the only difference there. So the molality is given to us. The the KB in this case is based on the solvent. so not the actual solution, but it's based on the solvent. So if you had an aqueous solution of this guy, most likely the solvent was going to be water, and you would look up this value in a table. And for example, the boiling point is 0.514, I think they give it to you for water, degrees Celsius per, and that's for water. So we would now have we have the molality given to us. So we could actually go into that equation where the change in the freezing point temperature would be 3 times our molality of 0.95 times our KB value that we would look up. Molalities would cancel, and we would end up with, in this made up example here, 3 times 0.950 times 0.514, and actually probably should punch it in right, would be good, times 0.514. There we go. And that gives us a change in the boiling point temperature of 1 point, if I punch that in right, 46 degrees Celsius. Just to make sure. Now, the important part, though, is, and what sometimes people mess up on as well, is that they get that number and they think that that is actually the boiling point temperature. And it's not, it's actually the change in boiling point temperature. So, because it's boiling point elevation, which means the boiling point of the solution that has that stuff boiled in it will be larger than the boiling point of just the water or the solvent by itself. The change in boiling point temperature is actually the temperature where the solution would boil minus the temperature of the pure solvent by itself. So in this case, since water was the solvent, the normal boiling point of water is 100 degrees Celsius. That means that if we put those numbers in, 1.46 degrees Celsius would be again our change in boiling point temperature, equals the temperature of the solution minus 100 degrees Celsius, which is again where water would normally boil. We would bring the 100 degrees to the other side, and that would give us 101.46 degrees Celsius is where this solution would actually boil. So the water by itself, without the calcium chloride in it, would boil at 100 degrees Celsius. By adding the calcium chloride in there, what we actually see is the boiling point goes up by 1.4 degrees, gets higher, because again, there's more stuff in the way. So it takes longer and harder for it to sort of get through and needs a little bit more energy. And it ends up boiling at 101.46 degrees Celsius, which is an elevation. Makes sense? Yeah.
Yeah, that makes a lot of sense. And so like I remember you talking about it in the previous lecture, where like you put salt into the water, and so it raises the temperature or the boiling point of it because there's more stuff in the way of it.
Yeah, that's pretty much how all these sort of properties work. Is basically the more stuff in the way, the more junk in the way, right? It basically gets in the way of the natural way that these things, the solvent like water, would naturally come together to freeze or naturally come together to boil. It's like putting like little roadblocks in the way, kind of, for that natural way that that happens. So it just takes them sometimes longer and harder to come together to freeze, for example. So it takes a little bit removal, more energy, or it takes it a little bit longer for it to boil, so it takes more energy to get them to kind of free themselves, because it has all this extra sort of junk in the way, if you want to think about it that way, that sort of gets in the way of the natural sort of process.
Is that the same thing when you put salt into the on the road so it doesn't freeze?
Exactly. So
Okay.
that's basically the other equation that relates to this guy pretty much identically, which is this guy, um, which is that, or again, if you're dealing with something ionic. And this is basically what is referred to, right, as freezing point depression, which means normally the water, for example, would freeze at 0 degrees Celsius. But by putting all this salt and stuff on the road, right, you're now getting all these particles in the way. So it actually needs to actually release even more energy for it to freeze, and actually lowers the freezing point. So instead of freezing, say, at 0 degrees, maybe it freezes at -12, or depending on how much salt and stuff they put on the road, or what the molality of it is. Maybe it goes to -5 degrees or stuff. So it takes a much colder temperature to get that sort of ice on the road, right, to start to freeze over and stuff like that. Kind of same idea. Sometimes people used to make like ice cream at home, right? You make rock salt, which is really just big things of sodium chloride and some ice and some water, and it lowers the freezing point. So you put the right ingredients in, you kind of can make like your own ice cream in a Ziploc bag and stuff like that. So the same idea. It lowers the freezing point and allows it to sort of freeze.
All
Now,
right, awesome.
freezing point is a little bit different because it is depression. It's different in this aspect of it, and that's important as we talked about for the sign. So when you do the change in the freezing point temperature, in this case, because the solution actually freezes at a lower temperature, you actually would do the temperature of the solvent minus the temperature of the solution. So opposite here. And that's important because that will get you the right sign, also allow you to subtract or add when you should. And again, so these two parts of these equations are really important as well, to make sure that you don't end up subtracting when you should be adding, or adding when you should be subtracting, is that relationship of those two things.
All right, awesome. Thank you.
You're welcome. Other questions I could help anybody with?
I'm currently in the process of trying to study for the final, and something I forgot was hybridization. Could you give like a quick summary?
Of hybridization? Sure. So hybridization is basically related to the electron pair geometry. And remember, the easiest way to sort of do it is you could literally just count it off. So if you remember, right, there's only one s orbital, and there are 3p orbitals, and there's 5d orbitals. So what hybridization is when we basically combo these atomic orbitals together to make those hybrid orbitals, which basically have the same shape and same energy, which makes for better bonding and stuff like that. So in a linear sort of relationship, when we think about electron pair geometry, we think about number of electron pairs, basically, right? And that basically has two electron pairs, which means if you just count here 1 and 2, you basically just hybridize an s and a p, and the hybrid orbital would be sp. When we have trigonal planar, again, this is electron pair geometry, that goes with basically 3 electron pairs. Doesn't matter if they're bonding or dots. And again, you could always start at the s and just count again 1, 2, and now 3. So we did an s and 2p, so it would be sp2. Then we get to tetrahedral, which happens with 4 electron pairs. And again, counting 1, 2, 3, and 4 gives us an s and 3p's. Then we got some of those exceptions to the octet rule, with those like triangular bipyramidal. I spelled that wrong. Bipyramidal. It's triangular, I believe. And that is 5 electron pairs. So again, starting at the s, 1, 2, 3, 4, and 5. We got an s, 3 p's, and a d. And lastly, octahedral is that also exception to the octet rule there. Has 6 electron pairs. Again, 1, 2, 3, 4, 5, and 6 would give us sp3d2. So that's the best way to do it. You would count them as electron pairs, just like you would be doing geometry, like we talked about. So that means if you had a double bond or a triple bond, you would count it as only 1 electron pair. And also, again, dots or lines, it doesn't really matter. You count them all. But again, double bonds, triple bonds, also still only 1 electron pair. And the hybridization is related to basically the electron pair geometry.
And for like, let's say a tetrahedral, what you're saying with the sp3, that's only for the central atom?
You could apply, technically, you can apply hybridization to outside atoms as well. A lot of times it is applied to just the center atom. But for example, if you looked at something like, say, this here, for example, let's just do that and do something like this. You know, so for example, if we went to this carbon here, it has one electron pair, two electron pairs. And again, this double bond would count as only one. The hybridization of this guy in the center carbon would be three, which would be sp2 hybridization. If we wanted to do it to the carbons on the outside, I'll just draw the outside one on the right there. It would look like this, right? Do that. So we got this guy at sp2. When we look at the carbon on the left-hand side there, it's got one electron pair, two electron pairs, three electron pairs, four electron pairs. So that would be sp3 for this guy. Same thing would be this guy as well. He would be sp3 because of that. 1, 2, 3, and 4. Now, if you wanted to, you could technically apply hybridization to the oxygen. Oxygen would have one electron pair, two electron pairs, and the double bond here would only count as one. So that's three electron pairs, which means the hybridization of this oxygen would be sp2. So most of the time, a lot of times questions in terms of hybridization will oftentimes deal with the central atom. But if you have more than one central atom, you could apply it to those guys as well. You could also apply, like I just did there, to the oxygen in terms of its hybridization. The only one you typically don't apply hybridization to is hydrogen because it only has one electron. So in order for this hybridization process, if you remember, there's sort of an electron that gets promoted up to a higher energy level. So since there's only one electron in hydrogen, we don't typically apply hybridization to hydrogen because it really won't hybridize because it only has one electron.
And the reason for this method of hybridization is so like you can make bound a smaller region where the sharing of electrons is happening compared to the s, p, or d orbitals that have like complex figures.
Yeah, so the simple explanation is that when we do this hybridization process, we end up, and I won't draw them correctly, but I'm just going to draw the hybrid orbitals as like these circles. We end up with these hybrid orbitals that are basically the same shape, and they end up, more importantly as well, sort of being on the same energy level. And that allows for, as you said, sort of better overlap that happens with those guys when they're sharing electrons, as opposed to if you think about, you're taking like say a 2p orbital, which has sort of this shape, right? And maybe you want to put it together with like a 3s orbital or maybe like a, or something like that, right? These guys obviously have different shapes. They're also on different energy levels. So it doesn't make for, in reality, sort of the bond angles. It doesn't account for sort of the bond angles that we see in a lot of these molecules that we know of. Because if you try to take like a circle and a figure eight and they're like different energy levels, they're not going to really come together nicely, I guess is a way to put it that. And this way is a way to try to, this hybridization way is a bonding theory that sort of helps us explain sort of the bond angles that we see and how these atoms kind of come together based on sort of the bond angles that we see. And it's based on the idea that, instead of trying to mix these atomic orbitals, which are like the S's and the P's, which are different shapes, different energies, we get these guys that kind of blend into these same shapes. And as they're blending, they're also kind of lowering the overall energy, which is always a good thing for bonding and allows for kind of better overlap to sort of occur between them. And there's also something we didn't really talk too much about in here, I don't think, this semester, but molecular orbital theory, which tries to explain some other things. So all these guys, sort of Lewis theory, hybridization, molecular orbital theory, they all try to explain some properties that we see in molecules that maybe one sort of theory doesn't explain perfectly or doesn't really account for things that we see perfectly, like just Lewis structures and that type of geometry doesn't necessarily account for always sort of the bond angles and stuff that we see. This sort of theory of bonding helps explain maybe some of those things. and why something like molecular orbital theory will help explain why when we think about something like O2, for example, it's a nonpolar molecule, but it has some paramagnetic properties, like it's affected by like positive, negative sort of charges. And molecular orbital theory explains that, because in the molecular orbital theory, it explains it actually ends up with an unpaired electron there that accounts for some properties that we see. And we didn't get into molecular orbital theory, but they each sort of try to explain a little bit of the properties that we sort of see in these molecules, because one sort of theory doesn't adequately explain everything that's been observed with sort of molecules and stuff like that.
Yeah, that helped a lot.